Hello, and welcome to this presentation relating to non-concurrent forces. In two previous presentations, we've considered coplanar forces, two-dimensional forces, that were concurrent, and we solved the various problems using graphical methods in one presentation and analytical methods in the second presentation. It strongly emphasised that you review both of those presentations before reviewing the contents of this presentation. What this presentation essentially does is consider various forces applied. We have a force at this point here, applied at this point here, force here, applied at this point, and finally a force here, applied at this point. What we instantly notice about these four forces is that if I draw lines of actions through the respective forces, we can see that lines of action of all the forces do not pass through the same point. They never actually cross at the same point. From the previous presentation related to analytical methods for solving concurrent forces, we used the tabular method to solve for the resultant force, and the first two columns shown in this table here for horizontal and vertical components we reviewed in that presentation. However, in this presentation, because we are now considering non-concurrent forces, we now have to review the moment consideration, so our table will be expanded with two further columns. And these columns essentially evaluate the moment about a point for the given system of forces. The mathematical content of this presentation is minimal. It's just a question of really multiplying two numbers together and summating columns of numbers. However, conceptually, most students find the moment aspect of the presentation very difficult to understand. So I'd encourage you to review the presentation at your own pace and make sure you clearly understand the concept of a moment about a point and how it applies in the tabular method we're going to use. Just an initial recap from the previous presentation. We need a notation for both force and moment calculations. The force notation was outlined in the previous presentation. It's shown below here. So our force sign convention we used stated that any horizontal component of a force moving from left to right was considered a positive component, and any horizontal force component moving from right to left was considered a negative component. Vertical sense, an upward force component was considered positive and a downward force component was considered negative. So that's the notation we will apply in this presentation related to resolving forces into horizontal and vertical components. This is a brief extract from the previous presentation, actually exercise 3, and here it shows a sketch of four forces in the various quadrants and how we resolve them into their horizontal and vertical components. If you take the 60 Newton force, when we resolve it into its horizontal and vertical component, notice these are right angled triangles here. The horizontal component is positive and the vertical component is positive. We resolve the 50 Newton force into its horizontal and vertical components of the right angled triangle. Notice the horizontal component is now negative, but the vertical component remains positive. Resolving the 40 Newton force in terms of its horizontal and vertical components. Now the horizontal component is negative and the vertical component is negative. And finally, resolving the 70 Newton force into its components. The horizontal component is positive and the vertical component is negative. If you're unsure about the use of that notation or the way we resolve the forces, I would encourage you to visit the previous presentation on force resolution. However, what we need to define now is a moment sign convention, and moments are always taken about a point, and that's very important. Whenever you specify a moment of a force, it has to be taken about a specific point. And as an engineer, we must always state what point we are taking moments about. Unlike the force notation, which we have positive to the left, negative to the right, positive up, negative down, with moments we simply have a clockwise moment, shown here, it goes into a clockwise sense, and that's considered to be a positive moment. And we have an anti-clockwise moment, shown here, and anti-clockwise moments are considered negative in our analysis. So that's all we need to consider as far as moments are concerned. Is the moment we're considering about a point having a clockwise sense, in which case it's positive, or is the moment about the point we're considering having an anti-clockwise sense, in which case it's a negative value? Just a very brief recap related to moments of a force. It's often convenient to consider spanners. And in the sketch, we've got a force F applied here, and it's applied to the end of the spanner. We can relate to this scenario. We realise the spanner rotates about a pivot point, sometimes called a turning point or a fulcrum, which in this case is the centre of the nut. So this is our pivot point. We're taking moments about that point. So this force has what's termed a turning effect on the spanner. Sometimes we call it a torque applied to the nut here. The turning effect is also called a moment, and the turning point, as we said, is sometimes referred to as the fulcrum. So in this particular instance, the sense of the moment about the nut would be in this direction. So that would be a clockwise moment, a positive moment to our notation. So a moment of a force, M, is calculated from the following formula. The moment about a point is the force, shown as 30 newtons in this sketch here, multiplied by the perpendicular distance from the fulcrum, about the point we're considering here. So by perpendicular distance, it's referring to this dimension here. This is the perpendicular distance to the line of action of the 30 Newton force. So there's a right angle here. We often label this distance shown as 0.1 here, the symbol D. So the formula we're going to use to calculate moments about a point is simply M is equal to F multiplied by D. So considering the spanner shown opposite, the F, the force, is 30 newtons. The perpendicular distance, D, from the pivot point, the nut in this case, is 0.1 meters. So the moment is simply the F multiplied by the D. So M is equal to 30 multiplied by 0.1. So 3 Newton meters would be the moment about the nut or the torque applied. And again, we can see the sense of that moment about the nut would be a clockwise sense. The bottom box here just shows applying the 30 Newton force at twice the length from the nut. So in this case, the force remains the same, it's 30 newtons, but the distance is now doubled, it's 0.2 meters. So obviously the moment applied about the nut is doubled, it's now 6 Newton meters. But the calculation for the moment is again the force F, 30 newtons, multiplied by the perpendicular distance away from the pivot point, labelled D, which is 0.2 meters in this case. So as seen on the previous slide, the turning moments we've considered so far have taken place in a clockwise direction, so they're called clockwise moments about the nut. In the diagram shown opposite, the force applied to the spanner produces an anti-clockwise direction. The force now is applied upwards here. So the sense of the moment would be in this direction. So about the nut, we now got an anti-clockwise moment. So as I said previously, moments can only be clockwise or anti-clockwise about the point we're considering. We're now going to use the moment concept to help us analyse the non-concurrent force systems we're going to review on the following slides. Example 1. We're asked to determine the magnitude, the direction and the sense of the resultant and the equilibrant acting on the components shown below. We've also got to find the perpendicular distance of the line of action of this resultant force from point A. So this cruciform shape that's shown here is actually irrelevant to the analysis. The shape doesn't matter. What is important is the location where each of the forces are applied. So force F1 shown here of 8 kilonewtons is applied at this point. We'll give them some geometry for that. Force F2, 5 kilonewtons is applied at this point. Force F3, 4 kilonewtons applied at this point. And force F4, 3 kilonewtons is applied at this point. And again, if we were to consider all the lines of action, we can see that lines never cross at the same point. So these are classified as non-concurrent forces, and that's what makes them more difficult to analyse. So shown in our table here, in the left-hand column we have the 4 forces applied in this particular case. And these next 2 columns, related to the horizontal and vertical components we considered in the previous presentation. When we're analysing concurrent forces, we're only concerned with resolution of forces. Unfortunately, with the non-concurrent forces shown here, we also have to deal with the moment resolutions. And that's what the second 2 columns here relate to. So what I would like you to do is to complete the horizontal component column and the vertical component column using your knowledge from the previous presentation. I have filled in the first row here to show you how the resolution of force F1 was undertaken. I will just consider F1 force resolution as a recap. Just showing the force resolution for the 8 kilonewton force F1. Here's our horizontal component labelled Fx and our vertical component labelled Fy, and the angle to the horizontal is 30 degrees. Don't forget, with this method we always have to consider angles to the horizontal, not the vertical. So from our previous presentation on concurrent forces, we know to resolve the horizontal component, Fx, that's simply the force multiplied by the cos of the angle to the horizontal. So in this case, that will be -8 multiplied by the cos of 30 degrees. Notice I've added the negative into the calculation because the sense of Fx is from right to left here. And from our notation on the previous slide, that makes it a negative horizontal component. So evaluating on my calculator, the horizontal component for F1 is -6.92 kilonewtons. Again, from previous work, we know that the vertical component, Fy, of this force will be F multiplied by the sine of the angle to the horizontal. Now we can clearly see that the sense of the component Fy in the vertical is positive. It's going up the page. So that will be +8 this time, multiplied by the sine of 30 degrees. My calculator, that becomes 4 kilonewtons. So that's force F1 resolved into its horizontal and vertical components. What I'd like you to do is now consider resolutions for F2, F3 and F4 and complete the table. As a check for you as you undertake your calculations for F2 to F4, I've stated the summation of the Fx forces at the bottom of the column here and summation of the Fy forces for your reference. I'd encourage you to start the presentation and resolve forces F2, F3 and F4 in the table. Solutions are shown on the following slide. Example 1 continued. Here's the full resolution of the forces in the horizontal and vertical components. I encourage you to check your values with that on the slide. If you're unsure about this force resolution, I would encourage you to revisit the previous presentation where we considered concurrent forces using analytical methods. Example 1 continued. So what we're going to do now is to consider the next 2 columns in the table. This is the new aspect of this presentation. Because these are non-concurrent forces, we now have to consider the out-of-balance moment effects that occur because of the location of the forces applied in our system. And as I mentioned in the introduction to this presentation, there's very little to worry about on the mathematical front. The calculations are simply multiplying 2 numbers together and summating columns. But what most students do find very difficult is the conceptual nature of calculating moments and deciding whether they're anti-clockwise or clockwise about a point. So I'm going to try and work through these solutions here in a very detailed manner. So hopefully you can apply the technique to exercises and questions that will follow. So let's consider the horizontal component for F1. That's -6.92 kilonewtons from our table. So there's the point of application for F1, and there's the direction of the horizontal component. Now, in all the questions we're going to consider, we're given in the question where to take moments about. As I said to you previously, you always take moments about a point, and these questions will specify the point. So the point we're considering here is point A, shown here. So whenever we're calculating moments, we need the perpendicular distance of our force about point A. So in this particular case, we've got the 6.92 kilonewtons applied in the sense shown, and the perpendicular distance we are about that point is 1 meter, shown here. So considering the line of action of the force here, this component, it's in the horizontal sense. So my perpendicular distance from that line of action and to the point I'm considering is 1 meter. So my calculation here is simply going to be the Fx force, 6.92, multiplied by the distance, and the distance is the y dimension here of 1 meter. Now what I need to do is account for the sense of the moment, whether it's clockwise or anti-clockwise. And just because the force is a negative force doesn't necessarily mean the moment is negative. We need to determine that for ourselves. So what we need to decide now is whether the moment is clockwise or anti-clockwise. So considering this force of 6.92 kilonewtons multiplied by this distance of 1 meter, the moment about point A would be in this direction here. So it would be an anti-clockwise moment. So we need to add a negative to our calculation. It's actually negative 6.92 multiplied by 1. Sometimes it helps by adding the spanner for the perpendicular distance to the line of action of the force. From the line of action, if we consider applying our force here at the spanner, we can clearly see it will rotate in an anti-clockwise direction about the nut shown here, which is point A, about where we're taking our moments in this case. So sometimes having our spanner positioned normal to the line of action of the force can help us in our understanding of evaluating the sense of the moment. Now let's consider the vertical component for F1. We've calculated that in our table is 4 kilonewtons. So that's 4 kilonewtons positive, so that's the force that's vertically upwards from the point of application. If we now consider the line of action of the 4 kilonewton force, we can see the line of action is vertically down through that point. So in this case, our perpendicular distance is shown to be here, and it's 0.5 meters from the diagram. So undertaking the calculation again, that's equal to the force is 4 kilonewtons. That's multiplied by our distance, 0.5 meters. And again, we must think of the sense, is it positive or negative as far as the moment is concerned? Well, this force multiplied by this distance will have a sense this way. So about point A, it will be an anti-clockwise moment. Again, we must add the negative into our calculation here. So evaluating negative 4 multiplied by 0.5, that's negative 2 kilonewton meters. Now some students do find it difficult to understand whether it's a positive or negative moment, but try and think of these perpendicular distances being spanners. If you think of the spanner context, then we're pivoting about the point A here, which would be the nut for the spanner, and then this force of 4 kilonewtons on the end of the spanner would be pushing the spanner around in an anti-clockwise direction. So sometimes considering the perpendicular distances as spanners and applying the force at the end of the spanner about the nut, the pivot point A in this case, sometimes helps you see whether you're moving in a clockwise or anti-clockwise direction. This can be a conceptually difficult aspect of the calculation for some students. Here is the spanner added as the perpendicular distance to the line of action of the 4 kilonewton force. So applying our 4 kilonewton force here and pushing on the spanner, we can clearly see it rotates in an anti-clockwise direction about the nut here, which is point A. Now let's consider the second force here, F2, which is a purely vertical force of 5 kilonewtons. So from our force resolution, by inspection, we can see that there's no horizontal component because a purely vertical force cannot have a horizontal component by definition. The 5 kilonewtons is a purely vertical component, which we can see by inspection. And it's positive 5 because it's an upward force, and that's positive to our sign convention. Also notice that the force is applied at the pivot point we're considering, point A. So by definition, there can be no moment generated if we apply the force at the pivot point. If we just go back for the spanner analogy for a moment, if I was to apply the 30 Newton force at the nut, then there's no way I can actually turn the nut because I'm applying it at the pivot point. I need to have some distance away from the pivot point, from the nut in this case, so that I can actually cause a moment to occur. So if we apply our force at the pivot point, by definition, no moment can occur. So in this particular case, there can be no moment in the mx direction and no moment in the my direction. And again, that's by inspection. If we now consider F3, if I take the horizontal component, it's 2.828 kilonewtons, then that's applied here. And if we consider the line of action of this horizontal component F3, we can clearly see that the line of action passes directly through point A, point about which we're considering. So again, by definition, there cannot be any moment generated by the horizontal component. So again, we can write 0 by inspection. If we now consider the vertical component for F3, it's 2.828 kilonewtons. Then its perpendicular distance from point A, shown here in terms of D, and from our geometry given in the question, that will be 1.5 meters. So about A, for the vertical component, we will have 2.828 multiplied by 1.5, again a force multiplied by a distance. We need to consider, is that a clockwise or anti-clockwise moment about point A? So looking at the force here applied at the end of our spanner, again think of the spanner as being the distance D, so the force applied at the end of the spanner here about the point A, the nut, would tendency to move in this direction. So that's again an anti-clockwise moment about A. So we must add the negative value to our calculation. So calculating that becomes negative 4.243 kilonewton meters. And finally, we need to consider the force F4, which is actually a horizontal force of 3 kilonewtons. We can see in our table, we've got positive 3 kilonewtons for the Fx, and we've got 0 for the Fy. Again, a purely horizontal force cannot generate a vertical component, so by inspection, it's 3 kilonewtons positive in the horizontal and 0 in the vertical. What I'd encourage you to do is to start the presentation now and think through the calculation for the mx value for force F4 about point A, and also for the my value about MA. See if you can determine what the force times distance will be in both cases, and also whether the moment generated about A is clockwise or anti-clockwise. The solution is shown on the following slide. So here are the full solutions for the moment of Fx about point A and the moment of Fy about point A. Here are the calculations for F4. I left you to solve for yourself. So the F4 horizontal component was 3 kilonewtons. So that will be 3 multiplied by the perpendicular distance, which would be 0.5 in this case. And is it a clockwise or anti-clockwise moment about point A? The moment sense would be anti-clockwise, so we'd have a negative 3 multiplied by the distance of 0.5. So that's negative 1.5 kilonewton meters. And of course, by inspection, we know that there's no vertical component associated with force F4. So therefore, there can be no moment My generated about A due to the Fy component. All we do now is summate the column for Mx, so the Mx summation shown here, and summate the column for the My moments. So the only reason we consider them as Mx and My is because we resolved the forces into the Fx and Fy. But actually Mx and My are both moments, and they can be added together to get a total moment about point A. And that's what's shown here in the bottom of the table. If we add up the Mx and the My to get the moment about Ma, we find we get negative 14.663 kilonewton meters. The negative value associated with the Ma means that the overall effect of the moments is in a anti-clockwise direction. And that's something we'll consider as the analysis proceeds. So that table to me is the most difficult aspect of the calculations we're really reviewing here. The force resolution is quite difficult. You have to make sure you think through very carefully whether it's a positive or negative component compared to our sign convention. But also the latter two columns, the moment analysis, is very difficult because it's not easy sometimes to understand whether the moments are clockwise or anti-clockwise about the point that's being considered. Example 1 continued. What we're going to do now is to use the two force components and represent them as a right-angled triangle. This is the process we undertook in the previous presentation related to concurrent forces. So if you reviewed that presentation, then this process is exactly the same as we used previously. We're going to draw a right-angled triangle for our components of Fx and Fy. Notice that the Fx in this case is negative 1.092 kilonewtons on our previous table, shown here. But I've drawn it in the negative sense from right to left on my diagram. So I'm accounting for that negative sense. So that's why I stated it as a positive value here. And also from the previous table, the summation of the Fy was 11.828 kilonewtons, shown here. Now that's a positive vertical component, so I've drawn that vertically up the page to our sign convention. All we've got to do is work out the resultant force, shown here. We need the magnitude, that's the length of the FR vector, and also the angle theta. From the previous presentation, we used Pythagoras theorem to find the resultant force. FR in this case is 11.88 kilonewtons. And we use basic trig, the tan function, to find the angle theta. Theta is 84.7 degrees in this case. So the resultant force is now calculated and shown on the diagram. If we want the equilibrant force, of course, then that's equal and opposite to the resultant force. So same magnitude but opposite direction. If you're unsure about the process required there to calculate the resultant force, I'd encourage you to revisit the previous presentation. Example 1 continued. Now this is a new part to the solution we didn't undertake in the previous presentation. We have to consider the moment effects from our calculations. What we're going to do now is to work out a distance d that the resultant force we calculated on the previous slide has to be positioned from point A to generate the moment that we calculated in the previous table. And essentially what we will do is end up representing the four forces shown initially in the question with one force at a distance away from the point A. This technique is used within industry to help simplify resolution of forces and analysis of structures. So we're going to calculate the perpendicular offset from point A. This is the process involved. We know from the previous table that the moment about point A was negative 14.663 kilonewton meters. Here's the moment we calculated in our table. We know the formula for calculating the moment M is equal to the F multiplied by D. So in this case, MA is FR multiplied by D. D is the offset. So to calculate the offset D from point A, we simply have to rearrange the equation. So D is equal to MA divided by FR. Simple transposition of this equation, dividing both sides by FR. Now looking at my diagram here, you can see that I've put the FR force to the right hand side of point A. What you must remember is when you've calculated the value of FR, it's defined. You cannot change it. So that FR direction cannot be changed. So the only positions I can put FR about A is as shown, or I could have put it this side of FR, keeping the same magnitude and direction, but my D would now be measured from here. But in our table, we know we have a negative moment about A. So when you consider the senses here, if I put the FR in this position about point A, that would have a clockwise sense, whereas this position of FR here about point A has an anti-clockwise sense. So that's the reason why the force was placed in this position, because I must generate a moment of magnitude 14.663 kilonewton meters, but it must be anti-clockwise about A. So back to my calculation. D is simply the M, and I put it in Newton meters now, 14,663 Newton meters divided by my FR, which is 11,880 newtons. That gives a value of D to be 1.234 meters. So I now know what the value of D is. So essentially what this process has done has taken this system of forces here, the four forces applied at various locations around our structure, and it simply replaced that system with this force located at this distance from point A. As I said, in some analyses in industry, that's a useful simplification that we can undertake. So what you've seen there is the entire process that's required in every question that we need to attempt. I'm going to now get you to undertake an exercise applying exactly the same process here with different figures and a slightly different configuration. But I'll now try and encourage you to engage with this process. The more practice you undertake, the more questions you attempt, the more the method will become understandable. So here's exercise 1 for you to undertake. Again, we've got to determine the magnitude, direction, senses of the resultant and the equilibrant forces acting on the components shown below. And we've also got to find the perpendicular distance, that's little d, of their lines of action from point B. So the difference here is we're taking moments about point B and not point A. So again, we've got four forces applied. We've got F1 is 2 kilonewtons. We've got F2 is 6 kilonewtons. We've got F3, which is applied at the point B, of 7 kilonewtons, and F4 of 5 kilonewtons. What I encourage you to do is to construct a table as shown on the slide here, and then evaluate the horizontal components, we call them Fx. Evaluate the vertical components, we call Fy, as we did previously. I've given the summation of Fx and the summation Fy for your reference. And then calculate the moment of Fx about point B, we call that Mx in this column here, and then the moment of Fy about point B, we call it My in this column here. Again, for your reference, I've given you summation of the moments about MB at the bottom of the table. I would now strongly encourage you to stop the presentation and attempt this question. The answers are shown here in the brackets for the resultant force and the offset. Use example 1 as your basic template to help you through this process, but the full work solutions will be shown on the following slide. So exercise 1, here's the solution, the full table calculated here. I would encourage you to stop the presentation and compare your values to those shown in the table. Don't forget we were taking moments about point B in this particular case, not A, as we did in the example. Very careful with the sense of the moments. Make sure you've got your positive and negatives in the correct place here. Always think of forces times distances about the point you're considering, about point B in this case. Exercise 1, solution continued. Here's our vector diagram that's been drawn using the summation of the fx from the previous table, summation of the fy from the previous table to draw a right angled vector diagram. And we've calculated the resultant force and the angle to the horizontal here. Exercise 1, solution continued. We're now calculating the perpendicular offset from point B. Trying to find the value of D, in other words, in this case. Again, notice from the previous slide the orientation of the resultant force. The 14.5 kilonewtons is in this sense on our diagram. And I put it this side of pivot point B because we have to generate a clockwise moment. Back to the table here, the MB is positive. That means it's a clockwise sense. And positioning FR this side of B gives us the clockwise moment. Had we put it this side of B, of course, we would have had an anti-clockwise moment. And that's not what we're looking for. So the calculation to evaluate offset D is exactly the same process as required in example 1. So I'll let you work through the calculations. You should find that D is equal to 0.398 meters or 398 millimeters. And once again, place this entire system given to us in the question with this force acting distance D away from point B. I will now leave you with some tutorial questions. Question 1 shown here. Exactly the same requirements as before. We've got to calculate the resultant and the equilibrant forces and also find the perpendicular distance from the line of action from point A. So we're taking moments about point A in this case. The answers are shown here. I've shown the summations of the fx, fy and the mx and my for your reference, and also the final answers for the resultant force shown here. I'd encourage you to start the presentation and attempt this question. I have shown on the next slide the full table of values that you need to calculate before working out the resultant force and the offset for your reference. So it's question 1, just a partial solution. I'm only showing you the table here. Here are my 4 forces applied. I'm working out my horizontal components, vertical components, mx and my moments. Just be careful with the angles used, because in the diagram F3 shows the angle of 60 degrees, but that's to the vertical. So in the calculations for F3, notice I've used the angle of 30 degrees because that's to the horizontal. So be very careful you'll use appropriate angles in your calculations. But hopefully the rest of the table you're able to generate. Again, where appropriate, you can state values by inspection. I would encourage you to do this. Where appropriate, you don't need to undertake the calculation in these particular cases. Put the answers down and say seen by inspection. Question 2 for you to solve. Answers shown again in the brackets. Be careful with this angle that's shown here of 20 degrees to the vertical. And finally, question 3, resultant force, out of balance moment and offset shown here. is the bibliography used to help generate this series of presentations. I hope it's been of help to you, and thank you for viewing.